SwayamPrabha. Digital India. Educated India.
Welcome to this lecture. We have been discussing about the hydrothermal processes and the hydrothermal deposits. We briefly looked at how to reconstruct or how to retrieve the physicochemical parameters of the hydrothermal fluid, temperature, even sometimes pressure, and gross chemistry in terms of the salinity. One thing is that all these diverse hydrothermal mineralization environment, one thing is very common, that these hydrothermal fluids, they do transport the metals in concentrations which make them deposit these metals in the form of deposits which are enriched and can be worked and can be recovered as ores for our use. The basic question that arises, that what makes these fluid transport these metals in whatever form, and we look at exactly in what form they are transported. And the analysis of the present day hydrothermal fluids from the ocean floor hydrothermal systems as well as the land based geothermal systems proves or gives us conclusive evidence that these hydrothermal fluids do transport the metals in substantial quantities, in concentrations, to give rise to mineral deposits. Although it always depends on how much or what is the quantity of the fluid and what is the concentration of a particular metal, that will vary from system to system. But the fact remains that these fluids, they do transport the metals. The question that is posed in this context is that what is the form in which these metals will be transported in the hydrothermal fluid. Let us see if it is possible that these metals could be transported as simple ions. We can write a reaction that PbS plus water Pb2 plus H2S in such kind of a situation, we can always quantify the concentration of the metal, for example, which is lead. This lead, its concentration will be actually be writing in terms of whatever oxygen species will come here. We can always write this, the K as the lead ion concentration here, and the fugacity of the gas, which is H2S over here. So, this will come from this equilibrium constant will be a temperature dependent one, and the value of this equilibrium constant will be somehow be related with the lead 2 plus concentration. So, if we think that this metal is being transported in the form of lead 2 plus, then we have to look at what are the values of the equilibrium constant of such kind of a reaction to conclude whether the lead will at all be transported as 2 plus ion? If so, in what concentration will be decided by this equilibrium constant value. What we observe is that this K value is so low that it leads to very negligible concentration, very small concentration of this ion as lead plus, or for that matter whichever ion we consider, lead, copper, zinc or any of the metals of our interest, are so low that if the metals are to be transported as metallic ions, then it will not be possible to get their deposits. So, it led people to do a lot of experiments on the hydrothermal experiments to understand the mechanism of solubility of these metals, and it was observed that these metals are actually not being transported as metallic ions, but they are being transported as complexes. So, the complexes means there are metals, we can call them as the charged metallic species as the metal ions, metals, and they actually combine with the, so these are generally positively charged, and this is here I think in this place here we can always make it a 2H plus kind of a situation, which would indicate also that it is happening in a low pH or acidic condition, which actually explains the solubility of the metals in a low pH or acidic kind of a solution. So, here the complexes, the metals are positively charged, and we say that they combine with something which is called the ligands, which are negatively charged, and these metals and the ligands, they combine in the hydrothermal fluid to make complexes. This, while the metals are the metal ions, the ligands could be simple or complex ions. Here, so without getting into the much of the theoretical details of such kind of metal ligand complexing, we will just see whether we will be we can rationalize or we can make some basic understanding on the transportation of the metals as metal ligand complexes. And essentially the question that arises is that what makes a particular metal combine with a particular ligand to form a complex. So, that means, or in other words, there is something which we will say as metal ligand specificity, or a specific affinity of a particular metal to a particular ligand. So, studies on this in this particular field, in this part of the solution chemistry, it led us to the concept of classification of the metals and the ligands into acids and bases, something similar to the Lewis acids and Lewis base, and the acids and bases were actually divided into hard, soft and intermediate. Hard, intermediate and soft. Similarly, the bases are also divided into hard, intermediate and soft. This figure here gives this table, which is shown on the this table shows a classification of the metals and the ligands into hard, borderline and soft. Intermediate is essentially borderline. So, which are the hard acids? The hard acids are the ones which have the high charge by radius ratio. They are the monovalent alkaline elements like the lithium, sodium, potassium, or the high field strength element like scandium, yttrium, tungsten, tungsten 6 plus, tungsten 4 plus. As you could see, a tungsten 6 plus with a higher charge has a higher charge by radius, and that is why is a much harder acid than even tungsten 4 plus. So, most of the metals of our interest, manganese, iron 3 plus, cobalt 3 plus, arsenic, these metals essentially having a very high charge by radius ratio are classified as titanium, zirconium, hafnium, molybdenum, antimony, platinum group of elements, uranium 6+, uranium 4+. These are all coming under the category of hard acids. The borderline acids are iron 2. So, obviously those which are the bivalent ones like iron 2+, manganese, cobalt, nickel, copper 2+, zinc 2+, lead 2+, tin, arsenic 3+. These are coming under the category of the borderline metals on the basis of their charge by radius ratio, and metals like gold, silver, mercury, cadmium, these are coming under the soft category of acids. Similarly, the bases fluoride, hydroxide, oxide, bisulfate and sulfate, where they are the complex anions. It is not an exhaustive list of the anions and cations. There are other ligands such as the organic ligands also could be incorporated here according to their, but then we are seeing the most common ones, and we see the chloride, which is the most soluble or the of the species in hydrothermal fluid, or the occurring in maximum concentration in almost all types of hydrothermal fluids, is coming under a borderline category. And bisulfide, sulfide, H2S, cyanide, bromide kind of cations are coming, anions are coming in the class of soft acids. Now, what does it tell us? Without getting into much of the theoretical details, it gives us a broad framework to understand that hard acids are likely to combine with hard bases to form their complexes. Borderline acids will combine with the borderline ligand to form their complexes. That is how we could correlate that lead 2+, zinc 2+, copper, they will form their chloride complexes, and soft metals like gold, silver, mercury will readily form their bisulfide, sulfide kind of complexes. So, this gives us a very broad outline, although the exact mode in which the metal is transported depends on which of the species are more dominant, and there is always a competition for the metals to be combined with the particular, say for example, experiments, and these also are very much dependent on the stability of such kind of ligands. For example, the sulfurous species will be very much strong dependent on the pH. So, depending on the pH of the environment, if there is a dominance of the bisulfide or the sulfide species, then only the gold or the silver or the mercury will get the opportunity to get complexed as bisulfide or sulfide. Otherwise, if there is a dominance in the chloride, and also these kind of complexes are a function, or the dominance of the type of complex which forms are a function of the temperature, and but within those limitations, these give us a good guideline to understand which of the metals are being transported in what form. So, it helps us also to subsequently, when during the deposition process, what kind of physicochemical change we would expect for the metals to be deposited, because this mineralization process involves the substantial solubility of these metals in the hydrothermal fluid under a given physicochemical condition, and we need to have a change to be brought about in the environment, the chemical environment, so that the metals will be deposited, and the metals, their solubility will decrease and they will be deposited as their respective minerals. So, here we can represent, this is the metal ion. So, the complex can be represented if it dominantly happens to be a chloride complexing, because the chloride complexing is the one which has been very extensively studied through experiments. So, this gives a schematic relation. The metal ion with Q plus charge and the number n number of the ligand with minus p charge will form a complex which is MLN Q minus NP. So, either it will be bearing a positive charge or a negative charge, will depending on the value of n, and here we can represent the equilibrium constants or the formation constants of such kind of complexes through generally represented equilibrium constant as beta n, which will be K1, K2, K3 or K4, which I will be just explaining in the next slide. So, here the concentration here is the combination is that suppose a bivalent metal with 2 plus charge and n number of chloride ion forms a metal chloride complex, then this will be forming a complex which will be MCl2 minus n, and the equilibrium constant is expressed as the concentration or the activity of this complex which has got a charge of 2 minus n, and this is how the concentration can be expressed. So, here if we take a sulphide like just the reaction that I wrote for the sulphide like galena, which is Ms plus 2H plus, is giving rise to a bivalent ion M2 plus and H2S aqueous. So, here the equilibrium constant is given by this expression, which is M2 plus into the. So, here these are essentially representing the terms which are the thermodynamic concentration or the activity, and in case it happens to be a gaseous species, we can represent it as fugacity or the corrected partial pressure, and if we take ideal conditions, then they all be representing a simple concentration terms. For example, for a metal it will be representing a concentration term as molal, or in case of a species like H2S we can always represent it in terms of atmosphere. And now if we try to find out that what exactly is the total amount of the metal M which is there in the solution, then we have to consider the metal to be present in the form of M2 plus and the total concentration of all the metals which is complexed in different stoichiometry, because this is a summation term. So, that means if happens to be a MCl or MCl2 or MCl3 and so on, then the total concentration will be coming out of all the complexes, possible complexes stoichiometry that is possible for a bivalent metal like, say for example, lead. So, here for the time being, even you can ignore this activity coefficient term, because we are taking them to be ideal and activity coefficient take them as 1. So, this becomes the total solubility become the activity of the metal ion plus all the activities of the chloride ion, or in terms of their concentration. Now, here we can replace, since the equilibrium constant through this reaction is coming out in the form of the H2S gas partial pressure, here we can replace M2 plus from this equation as the equilibrium constant into the hydrogen ion concentration square divided by the fugacity of H2S, and this gives us an expression. So, this is a total concentration of the metal. So, as we stated before, that if we consider the metal to be transported only as metallic 2 plus ion, and the because of the equilibrium constant, very low equilibrium constant of these kind of reactions, but in actual what is happening is that this metal like M with availability of the ligand which is chloride is able to form complexes, and the total solubility of the metal is contributed by formation of the complexes of the metal. Here is the example that take a metal like lead. So, here this is the solubility product, which is the activity of the concentration of the lead 2 plus and the fugacity of H2S by the activity of hydrogen ion square, and the total concentration of the lead expressed as molal is given by an expression where it is the solubility product of this reaction into the pH divided by the fugacity or the partial pressure of H2S. So, what is coming out from here? It gives us a clear cut idea that the solubility of the metal is dependent on one of the important parameters that comes here is the pH. So, the pH has to have the value which will directly so when the activity of H plus ion will be directly responsible to what the concentration of the total metal is, and other variables are also contributing to it. Now, coming to the actual mechanism, taking the example of lead here. So, if we consider that lead is a bivalent metal, and in a hydrothermal fluid we have abundant chloride ion as the complex as the ligand, then lead can possibly form a series of such complexes as a lead Cl whole plus, lead Cl2. This is actually this is PbCl2. There is a mistake there. So, Pb2 plus 2Cl minus, this will be PbCl20, and in this case, so I just correctly write it out here. PbCl plus, lead plus 2Cl minus, PbCl to 0, lead plus 3Cl minus, PbCl3 minus, and lead plus 4Cl minus, PbCl4 2 minus. So, these are the correct species which form as the complexes for lead. So, if you could see on this, so then here the total concentration of lead here is being shown as the total concentration is coming from the molality, the concentration of lead in the form of lead 2 plus, lead Cl plus, lead Cl2 0, lead Cl3 minus, and lead Cl4 plus. Now, this can be expanded in the form, because for each of these complexes, lead Cl plus, lead Cl2 0, and lead Cl3 minus, and lead Cl4 2 minus, we will have they can be related to the concentration of the total chloride MCl in terms of molality of chloride with the formation constant like K1, which is for the formation of this lead Cl, K2 or is represented as in general term as beta 1. So, beta 1, beta 2, beta 3 and beta 4 with the concentration of the ligand, which is your chloride over here. So, now we can make out from here, and again we will replace the molality term, molality for lead plus, as a solubility product of the reaction, which is lead sulphide plus H plus giving rise to lead ion and H2S. So, here we will be replacing the H2S term here. So, the total solubility of lead in the hydrothermal fluid will be contributed by these many factors, out of which something which is coming out to be very, very prominent is that the concentration of the chloride ion. So, the amount of the metal, taking example for a metal like lead here, and the situation would be similar for other bivalent metals like zinc, is also that the solubility, the total capacity or the capability of that particular fluid to transport lead soluble form to give rise to a mineral deposit finally when it gets deposited is depending largely on the concentration of the chloride ligand. So, even if this is only expanded in the form of the activity coefficient, which are all taken as 1. So, if you take the activity coefficients in this equation all as 1, it will be reduced to this equation only. Okay, so likewise, there have been several experimental study on the solubility behavior of gold as different complexes as chloride and bisulfide, solubility of many of these base metals copper, lead, zinc in hydrothermal fluids in different wide range of temperature and composition, mainly affected by the pH. So, there is a good amount of knowledge and data and information that is available to us that under diverse type of ore forming environments, hydrothermal environments that we have discussed, the metals are dominantly transported in the form of metal complexes, like chloride complex is one such dominant metal. There could be bicarbonate complexing, there could be bisulfide, sulphate and other type of complexing depending on the gross chemistry of the fluid. So, in order to get the hydrothermal fluid deposit in the form of a mineral deposit or an ore body, we need to have a change in the physicochemical environment, change over from a dominantly from a transporting regime to a depositional regime. So, this is brought about, as we have already discussed before in the context of fluid inclusion, that they basically brought about by processes boiling of the fluid, mixing of the fluid unmixing or phase separation and interaction with the wall rock. So, these maybe that they operate in combination, and then as we stated in the very beginning regarding the ore deposits, that these processes have to operate at a particular scale and in an optimum intensity and in an optimum environment, which will give rise to a hydrothermal deposit of a size in terms of its the quantity of the metal that will be deposited in a particular locale to give rise to a deposit. Sometimes they do give rise to deposits which are fairly large in size, giving a good amount of the metal in terms of the total tonnage that is available, and sometimes if the conditions are not that very favorable, they result in what we call as a lean or not so rich mineral deposits. So then if we want, so now once we are going from a transporting to the depositional regime, then we see that what exactly we would expect. For example, so the hydrothermal mineralization as a whole, on the whole, whenever the fluid is transporting the metal, where the temperature it could be because if it is temperature dependent, temperature is higher. If its pressure has got, because we will see the role of pressure again sometime in the course of the lecture. The oxidation state, if it happens to be a more near surface, it is the EH-pH conditions and so on. And then when the deposition is taking place in any locale, here we would expect a gross difference in the chemistry of the fluid and the country rock will be in gross disequilibrium with each other. So they would the fluid when it is depositing the metal will leave its imprint in some form, which we broadly categorize as the hydrothermal alteration, which we will be discussing in detail in the next class, but just to give an idea. For example, any metal which is being complexed as MClN Q minus N kind of a complex, and that is now coming in contact with, or that is now coming to a situation where there is the partial pressure of H2S has increased to the extent, even though I am not writing any balance equation here, I will simply just put it as MS. If this particular complex of a metal chloride is getting sulfidized to give rise to the metal sulfide as MS, then it is definitely going to liberate this species in the solution. So as a direct consequence of deposition of this metal complex to a sulfide, there will be release of this H plus in the fluid. So in order for that particular reaction to advance or to go on to completion, there must be something which will absorb this H plus, or which will act as a sink for this H plus to be accommodated. So that possibly is only will be done by the wall rock, and in this process the hydrothermal, this whole spectrum of hydrothermal mineral deposits that we have listed out in the beginning, the magmatic, the metamorphic, the surface operated volcanogenic volcano associated epithermal deposits, or the volcanogenic massive sulfide deposit in operating in the sea floor mid-oceanic ridge systems. All these systems are very characteristically associated with something which we call as hydrothermal alteration. If we see it here, so the consequences, immediate consequence of the mineralization, hydrothermal mineralization process results in something called hydrothermal alteration. So this hydrothermal alteration, the nature of the hydrothermal alteration, the exact mismatch in the chemistry of the wall rock and the hydrothermal fluid, and what exactly happening in terms of formation of the secondary minerals in the wall rock as hydrothermal alteration zone, whether they will be occurring as a single zone or multiples of such zones arranged in space. We will look at them individually when we look at these deposits, but these hydrothermal alteration zones are very prominent in deposits like porphyry copper deposits, skarn deposits, the VMS, the lode type deposit, the epithermal deposits, and there are some nomenclature which are proposed for such kind of hydrothermal deposits, like potassic alteration, phylic alteration, argillic alteration, propylitic alteration, advanced argillic alteration. These alterations are all terminologies associated with the porphyry copper deposits in the convergent plate boundaries like the Andean margin. So, potassic alteration is one which takes place when the pH of the fluid is rather high and it is in the potash feldspar stability field, temperature is high and it is the original magmatic fluid at high temperature, and gradually when the temperature is decreasing and the fluid is interacting with other fluids like a meteoric fluid source, then it is giving rise to alteration zones which are dominated by minerals, which is sericite, or sometimes even the, and also it does indicate that the alteration zones are developing as a function of the increasing water by rock ratio, and we will look at the details of the, and there are many other types of alterations which take place in many different deposits, like the skarns are characterized by very typical alteration. There are sometimes addition of silica in the form of silicification, addition of carbon dioxide and formation of the carbonate, late carbonate type of alteration, and we will look at them. And so in summing up for this week's course, that we looked at the sources of hydrothermal fluids, different possible sources, their gross chemical and thermal characteristics, how to retrieve the information on the physicochemical parameter by studying the mineralogy, by studying the fluid inclusions in them, and got a brief idea about the mechanism of transportation of the metals in hydrothermal fluid and deposition. And we will see the individual types, the different types of alteration zones which are associated with this deposit in the subsequent discussions. Thank you.